So hi everyone, welcome to the presentation. My name is Balázs Kreith. I am software architect at Upcounter Finago, and today I'm going to hold a presentation about concurrency based on the book of Clean Code by Martin R.C. And this is the last chapter, although to be honest, my personal feeling is that this chapter would actually deserve a book or several books. So let's try to concentrate on the basics challenges and the tools and some factor we need to consider when we are talking about concurrency. I followed in this presentation. I followed the book. It's going that why concurrency, why we are talking about. What are the myths and misconceptions we need to actually clarify? What is the concurrency defense principles? How to design an application or any kind of things which is for concurrency? What are the tools for the concurrency usually available in every kind of programming language we need to be considered? What is the synchronization? How to synchronize? Writing a current shutdown code, which is actually a separate book, but this is a separate subsection. Testing the threaded code and some conclusion. So let's start. Why concurrency? What is concurrency? Is that the book definition says that concurrency is the decoupling strategy. It helps us decouple what gets done from when it gets done. What is this meaning? Let's say Alice wants to sleep. Alice have a bed. So the resource owned by Alice, and she wants to sleep. What gets done when is actually kind of tied together, right? Let's say Bob comes into the way, and he wants to sleep also. So we want two bed, right? Because two resources needed. But what if Alice actually wants to sleep at, let's say, in the night, and Bob wants to sleep in the day? Then one bed is enough, just need to be scheduled, which means that we have a shared resources. It's beneficial, it's cost efficient, and we don't actually have to keep two beds. It's one bed enough, and everybody is happy. The problem comes when Alice wants to change the sleeping habit and wants to sleep in the day as well, right? And what if more and more people wants to use the beds? One bed is not enough, so we can provide many beds, but we don't have to provide as many beds as the people wants to sleep. That's meaning that what we decouple what gets done and when. That's the resources. The resources are the bed, and the processes are the sleeping, and the man, and who wants to use it is the man. Okay, let's put it in some kind of more abstract way. When we have processes and we have the time, if we have, let's say, a database connection and we have one instance of the database connection, then we see that this process is using the database connection in this time. Single process, dedicated resource, easy. Now, two processes wants to use the database connection. We can create two instances, multiple processes, dedicated resources for each processes. We are talking about parallelism. Then we say that, then we say one instance of the database connection is enough for actually serving two connections. Then we say multiple process, shared resource. This is concurrency. And as we see that, let's say, three processes wants to use the database connections, shared resources because two instances available, multiple process, shared resources, S is actually missing. This is concurrency. Okay, so as we see that this is kind of optimization and scheduling technique that we need to use as less resources as possible, but in a way that everybody needs to every process needs to accessing to the shared resources. This is kind of maybe easy to understand. What are the false myths and misconceptions based on the book? Somebody says that concurrency always improves performance. If someone says that if we are introducing database connections, many database connections, or we can share the database connections, and it's always improve the performance because more processes can access to the same database connections, maybe he is false. Because if, let's say, two processes uses the full time of the database connections, if you're introducing the third processes, that doesn't solve any problems, right? It's just actually making more. Design doesn't change when writing concurrent program. No, in fact, it's actually changing dramatically, because you need, for instance, first decoupling the resources which is owned by an object when you are writing something, some processes, some functional objects, something which uses the resources. Those resources needs to be shared. And sometimes it's not created on the constructor of the processes when you are actually creating those instances which is using that resources, but is created outside and passed through some kind of mechanism. So that's actually changing the design. The other flaw is that understanding concurrency issues is not important when working with a container such as web or a AGB container. It's not true. You need to always be aware what you are using, what is the capability. You cannot overuse it just because you don't have to write the concurrent code yourself. What is true is concurrency incurs some overhead. Yes, it incurs, because the resources are shared, and you need to ensure that the resources are mutually excluded. For instance, that's one overhead we need to consider, and some other which I don't know now, but you will face it. Correct concurrency is complex. Yes, even a simple program when you are writing two processes which is sharing the resources is complex. We will see why. Just one example is that shutdown. You need to shut down both processes, and you need to ensure that those processes actually release the resources. But since the resource is shared, who will close the resource? Oh. Sometimes. Yeah. It has a log. Yeah. Concurrency often requires a fundamental change in design strategy. True. See microservices. Microservices, by the way, a concurrent thing that you are creating many services which is using their own resources as own databases, but they are communicating and they are using, for instance, a shared resources like let's say a Kafka or a message broker system. They are using all this kind of shared resources to communicate to each other. That's a communication. But other than that, let's say that microservices using a global database, which is a bad design practice, but it's possible. But you are into using more and more services, which are microservices. That's actually fundamental change in the design strategy. You had a monolithical application, and then you are moving into the microservice application just for concurrency, because you want to exploit the possibility of the microservices, and you want to achieve something using concurrency. So how can you design an application which is capable of, how can I say, handling concurrency in a correct way? Uncle Bob, not so long ago, in the book, it calls that using the single responsibility principle. It's not it's not a principle for concurrency, it's a principle of designing an object. But this principle must be used in concurrency. And what is this meaning, that single responsibility principle? Is that your object needs to be responsible as less as possible, needs to own as less as possible resources, as less as possible fields, as less as possible methods. The class should have only one reason to change. I said that as less, so narrowing down. You don't have to widening open your object. If you want to add a new feature or a new functionality, maybe you consider to add a new object or something. But the thing is that only one reason to change the class, the own resources. And although because of confusion around the word reason, it is stated that this principle is about people. This definition came from the not latest, but few years ago he wrote a blog post. So it's not coming from the book, but Uncle Bob has a blog post, and it's coming from there. This quote. In other words, keep your concurrent code separate from other code. enclose your shared resources and the object which is on the shared resources or handling the shared resources from any other codes. So what are the corollaries of this principle? Limit the scope of the data. Your resources which is shared needs to be limited, and the scope which is actually accessing it. Use copies of the data. It's another thing is that if the shared resources are used somewhere, you may want to consider that you may copy those data to not to access to the same resources. Like, let's say that Lambda architecture, if you heard about it, that immutable data are processed by two separated microservices. They are not changing the data, and they are using the same data, but the copies of the data, because they are immutable. Functional programming, for instance, when you are calling a function in another way in the parameter, it's copied. So you will not have the situation when you have some kind of conflict between the processes just because you may be changing something, although you shouldn't changing because it's immutable in functional programming, especially. But as much as possible, copies the data when you don't have to change it. For instance, copies data gives you parallelism. If you have two processes which is operating based on the data they are getting as a parameter, you don't have to get a pointer. You may get a copy of the data. It works. If the data is not so big, and you don't have to involve like gigabytes of copies, then it might worse do it, right? And the third corollary, come on, you can do it. Threads should be as independent as possible. Yes. Threads shouldn't communicate all over each other just to asking something, because the thread communication has an overhead, has a delay, has a log. It needs to signal the other thread. The other thread needs to wait for the signal. All of these interruptions, all of these logs are involving overhead, lags, and possibility of failures. So your thread we can talk about, for instance, actor framework or design principle. In an actor framework, the actors are separated threads, and all of the actors have mailboxes, and the mailboxes are messages from another thread. Only on those mailboxes you can send any kind of messages to the other thread, which means they are not blocking each other, they are not waiting to each other, they are processing their operations independently to each other. That's in that way the threads are as independent as possible, but your thread should be as independent as possible when you are introducing it. So, tools for concurrency, the next subchapter for this chapter. How can you achieve a clean code for concurrency? Well, obviously you need to provide it thread-safe collections. Please do not invent yourself. Basically, the thread-safe collections, for instance, in Java or in C# or in any kind of languages, it's not accidental. Use it. Don't invent yourself. Use the executor framework for executing unrelated tasks. It's kind of maybe a bit Java specific, but I'm sure that in C# or in .NET have the same framework to executing asynchronous tasks. So it's not Java specific, I'm sorry, it's just in Java it's called executor. Use non-block solutions when possible. Yeah, blocking is the main problem. If we go back to here, if you see that the shared resources in process 1 and process 2, there are overlaps a bit here and here and here maybe. It is impossible to use the shared resources, the same database connection by two processes, so it's a mutual exclusion. And then this processes needs to wait until this is finished. This is called, I mean, this you can achieve by using locks. But where is it? Use non-blocking solutions when possible. In that case, when you are talking about database connection, that is, and you share the database connection, that is inevitable that you need to wait for one process to finish their work before the next process is started. But when you may using some kind of solution which is not involving locks, like producer consumer, when you are communicating between two threads, that's non-blocking in a way that when you are writing into the buffer, the consumer can read it. But that's also actually involves block, because when the buffer is empty, then the consumer is waiting and blocked. But copy of the data, for instance, it's not blocking. So if you have thousands of processes and they need to actually calculate on some kind of fraction of the data which is passed to the parameter, then the best solution is to copy of the data, and they don't blocking each other because they are not locking to each other to accessing to the data, for an instance. Parallelism is the best way to achieve the throughput, because if everybody has their own resources, then the processes are free to do everything with the resources. In general, I would say that put the competition between the processes as far as possible. Like in database connection is the good way, that the database in the concurrency is done in the database. You can create many instances of the database connection. They will go into the same database level, and they will competing to the database there. Or if the database is the bottleneck, or database connection is the bottleneck, then that's the point when you need to put the concurrency. Just put the concurrency as far as away from the processes, and use as much as copy as possible for achieving. Several library and classes are not thread safe. Yes, that's true. The basic collections, for instance, in Java, the list are not RI list is not thread safe. You need to use the blocking linked list or blocking queue to achieve thread safe collections. Know your execution model. How you can communicate, how the threads are communicating to each other, how the threads are accessing to the shared resources, to the shared data, are a principal design point. Then we can talk about producer, consumer, we can talk about reader, writers, and dining philosophers. Producers, consumers involving, there is a producer which is producing the data, there is a buffer which stores the data which needs to be consumed by another thread. You can achieve by, for instance, the blocking queue, when one producer is dumping data to the buffer, let's say something, I mean bounded buffer, and the consumer is consuming from that buffer. Now, what is a good way? A good way if the consumer is faster than the producer, you can introduce more producer, and then the throughput is kind of balanced. If the producer is much more faster than the consumer, you are introducing more consumer, right? But that's meaning that some data, it's very good for stream processing when you have unbounded data which needs to be processed, which needs to be aggregated or something. Then you are putting the data, the samples, the measurements into the buffer, and the consumer or consumers pull it and then processing it. Readers and writers, when it's basically for throughput, because in several occasions when you are locking the data, you lock everything and no other thread can access to that part of the memory, for instance, then just only one. It's a pain when you have several processes, just wants to read the data, doesn't want to change, just want to read it, but only one can access it. Let's say database collection, because in database we have read and write logs separately. If several processes just want to select the query and then give it back to the request processes, then those are just want to reading, doesn't want to change anything, but the writer. So how you can achieve greater throughput and allowing several thread to reading, but but ensuring that only one can changing. You can use reader-writer locks. So you are specifically say that this thread wants to access this data just for reading, and all of the threads which is accessing the data just for reading can access to the same time. It can overlap to the access, but whoever says that I want to writing, that thread needs to wait until every reading thread finishes the work. What is the catch-up? What's happening when one thread is actually never finishing the reading? One processor says that from the constructor of the object that yes, I have a reader lock, and then I am doing my loop forever. Then the write will never happen, right? On the other hand, when several read thread waiting for reading, but you have a request to writing, right? How do you prioritize it? That's actually a responsibility for the underlying layer, but maybe when you are writing your concurrent code, it's responsibility of yours to prioritize the writing on the reading. So, or you prioritize the reading, it's up to you. But this task needs to be considered when you are designing the reader-writers. Once again, producer-consumer is using a buffer between the threads to communicate and processing. The consumer is processing. Readers-writers accessing to the same part of the data, but in a different purpose. And dining philosophers is when you have, let's say, m resources and you have n processes, n obviously not equal to m. Usually m is smaller than n, so less resources than processes, and they want to use those resources. And let's call it a chaos, but it's dining philosophers. When you need to ensure that the philosophers always have resources. I mean, the processes always have resources. In other way, if we are going back to the bad situation, and we are talking about this, when the number of beds are smaller, let's say 10, and the number of people are 20, maybe 10 bed is enough for 20 people because they want to sleep in a different time. But if one people cannot get bed at the time he wants it, then you need to increase the bed. You need to increase the bed until actually everybody will have the time for sleeping. Okay. Synchronization. How you can synchronize the data? There are 3 methods available when we are talking about, let's say, a client-server architecture. One is one philosophy says that client-based locking. When a client wants to access to the server, when the client gets the portion of the time slot from the server, it locks the server, and then that's it. The server-based locking is that the client wants to access, every client's competing it, and the server will locks itself, so it will decide which client will actually access, and doesn't get maybe a portion of the time. Some clients will be served faster, some clients will be served slower. It depends on. Adapted server, when you putting a layer between a client and the server, and the adapted server will lock the server, and the client will access to the adapted server. You have an additional layer between them, and that additional layer is a proxy, and that proxy is responsible for locking the services. Maybe the server is actually designed for one thread or one client, and the adapted server is just only doing the thing is that one client request goes, or maybe it's actually prioritizing it. You have an abstraction level then. Keep synchronized section small. The book uses Java code samples. In Java, it has the keyword synchronized, which is lock for the object. It uses the object this. I mean, if you are using the object, this object to lock, it locks this object, and only one only one who is that this object is shared, so the object itself is the shared resources, and the synchronized keyword logs these resources to use only by one thread and mutually one thread. Now, why I put it in here, and why I didn't put it into after the public synchronized void? Because if you have some kind of out of the concert of this object, like some kind of processes which is out of the access of the shared data. Let's say you have a kind of user rights check, you have a kind of other processes to do or checks before you accessing to your own resources, then it takes time. Why do you actually log the shared resources when you don't use it? And also it's a fail point, because if one of the check is actually failing and then you will throw an exception, for instance, and then exception is not carefully handled, then of course actually if you are using the synchronized keyword, the lock is going to be released when you are going out of the scope, but it's just log the object in an unnecessary waste of time. So, and also it's a failure point, because if for one other reason one check is failing and you don't access to the shared log, then why you actually logged it? Other processes wanted to access it. So keep your synchronized, and that's why I put it in the synchronized keywords into here, as close as possible to the point when we are when we are accessing to the shared resources, shared data fields. That some people sometimes I see the mistake that oh, we have a synchronized keyword, so let's put it everywhere. Let's put it in every public method, then we will not have a problem. Yeah, but you will actually locking every kind of public method, and then one public method may be actually accessing to the other public method, which is also synchronized, which is also low. So, why? It doesn't have a sense. It's actually it's in the myths, right? Because they say that, oh, if you have a AGB container, you don't have to know how the threads are working. You need to know that you are mutually exclusion you are using, and that resource is actually it's costly to use it. So synchronized keyword is very good because it's ensuring you don't have to lock the resource, you don't have to lock the object, you don't have to release the object. It's automatically doing even if you have an exception. But still you need to know what you are doing. And the single responsibility principle says that as less as possible. Writing correct shutdown code. Yes. writing concurrent application when it is in your head. For instance, let's say we are writing a producer and consumer. That for instance, let's say you are writing a REST API. REST API is a producer because it's just accepting any kind of request from outside of the world and putting the messages into a queue, and then from that queue somebody is catching it up. Now it's beautiful thing that you can say that, yeah, let's do then a two-threaded application. One thread is actually receiving anything from the REST API endpoints, and the other thread, and then we are using a queue, a blocking queue, and the REST API thread process is dumping the measurements and the requests to the blocking queue, and the consumer is actually consuming it and processing it and doing whatever we want. Okay, if it is in one application, how do you shut down the application? Because that's not trivial. Yeah, as I said, let's say we have a producer, let's say we have a blocking queue, let's say we have a consumer. If the blocking queue is empty, the consumer is waiting and blocked. If the blocking queue, whenever it's full, if there is an upper bound, then the producer is, by the way, blocked. But the problem is here we are facing is the shutdown. So let's say we are shutting down now the application and the blocking queue is empty. The producer, the producer and the consumer send a signal, but the producer got it, so it's not producing anything and shutting it down. But the consumer cannot shut down because the blocking queue is empty and it's waiting. It cannot receive any kind of messages, it cannot process any kind of messages because it's waiting for messages from a blocking queue, but it will never happen because the producer is actually shut it down. You need to consider this kind of situation when you are writing an application like this. Usually the solution for this kind of situation is called like using a poison pill. The producer got the shutdown signal and putting a poison pill into the blocking queue, and when a consumer receives it, it's known that it needs to shut down. That's one. That's why it's a shutdown. Writing a correct shutdown code needs to be a kind of consideration, not just killing the signals. And if you're killing the signals, so you are aborting the threads, and the blocking queue was not empty, and the blocking queue relied on the memory, then maybe you lost business critical data because you just shut it down everything and then it went away. You shut it down, the consumer, but who consumed the data, right? That's why the poison pill is a good solution, because that's going to be the end of the things. You ensure that everything is processed. Consider how the code is used. Writing a test, it's a general purpose. I would say that when you are testing, you need to think of some otherwise when you wrote the code. And the typical example I would usually say is that using a BDD, which is behavior driven test, then you are not thinking about how you implemented the code, but you are thinking about how the code is used, how the customer is going to be used, how to crash it. And when you are writing tests for the thread concurrent applications, you need to consider how will you use the concurrent application, how will you use the concurrent resources, shared resources. And there's a thread spurious failures as candidate threading issues is one aspect you need to consider. And get your non-threaded code working first. Yeah, when you think about, let's say, back to the REST applications and processing the requests from the REST applications. First, if you are writing the code in one thread, so you get the request and you're processing it. If you get it work first, then you can decompose the processing of the requests from the moment when you got the requests. This is about that. Make your threaded code pluggable. Yeah, using some kind of, for instance, producer or consumer, then it's pluggable because you are plugged to the blocking queue, and it's easier to test it because then the thread is separated, independent in a way. I mean, as independent as possible. If you want to test the consumer, you don't have to make the producer because you can fake the producer. Make your threaded code tunable. Yep. For instance, the consumer, you need to kind of cloning the consumer because you have more data to consume than, or the producer, if we are talking about that example. Come on, run with more threads than processors. Yeah, well, it's stress load tests, but usually it was the effort. Run on different platforms. The code is written in 2007, but it still remains that if you are running on a Windows machine and if you are running on a Linux machine, then the behavior or scheduling might be different. How the operation system is actually creating the thread, how they are using it, how they are executing it, it's all over the underlying responsibility of the operation system, and maybe it's different. So you need to kind of writing tests for that. But it's a regression test. Instrument your code, try and force failures. it's a principle of that of testing your code is that let it crash. Don't afraid to be crash. That providing malformed data, not just form data, providing idiot things, what you have never done it because you know how you implemented the code, but who will use it? It can happen. Yeah, and some conclusions about the chapter. It's highlighting the things we have talked about so far. Is that know the possible source of concurrency, follow the single responsibility principle, know your library, know your execution model, write a proper shutdown mechanism in testing the system in the aspect of failure. All of these aspects needs to be done, considered, and followed if you want to write a clean code. But it's a kind of general, right? You just need to be aware. Anybody, in my personal opinion, anybody is actually facing or writing a concurrent application. I mean, application which is using concurrency, facing these kind of issues. It just needs to be highlighted that it needs to be followed. Feature shouldn't be added to the object which is sharing or owning the resources. It needs to be another object. It needs to be keep into your mind. So that was the book chapter about, as far as I have read, and yeah. Thanks.